Hello, my name is Jason Martino, and I am here on behalf of Robotics Engineering 3001 Team 11 to present our final project implementation. For our final class project, we were tasked with sorting multicolored 3D printed orbs with a 3D printed 3 degree of freedom robotic manipulator. Firstly, in our implementation is the hardware section. As mentioned during the exposition, our robot was largely composed of 3D printed elements. It also utilized 3 large servo motors to create the joints of each of the mechanisms and give the robot the 3 degrees of freedom it has in its movement. It also used 1 smaller servo to actuate the 2-point claw gripper that was used to pick up the 3D printed orbs and sort them throughout the process. On the electrical and programmatic end, we used a standard breadboard to wire the Itsy Bitsy microcontroller to the 3 respective PWM wires controlling each of the 3 joint angle servo motors. This board also encompassed the button and wiring required to move the robot through its calibration procedure. Next is robot control. For our 3 degree of freedom robotic manipulator, we utilize the Denevit-Hartenbaugh or DH convention to assign frames and parameters and compile a table of elements that would allow us to better understand our kinematic control functions. We used forward kinematics, which involves conversion from joint space to task space, inverse kinematics, which is the opposite, and differential kinematics, which is used to control the velocity of the end effector through monitoring joint angle velocities to create smooth robot motion throughout our robot's workspace. Our system utilized computer vision to detect, localize, and acquire the orbs while in the robot's task space. We first intrinsically and extrinsically calibrated our camera utilizing a number of camera parameters and the complex combination of multiple matrices that allowed us to take pixel locations and turn them into real XYZ coordinates in the robot's workspace. From here, we performed well-known computer vision algorithms such as erosion, dilation, and color masking to distill out the ball from any other objects or noise that were present in our camera frame. Everything mentioned up until now was controlled by a complex hierarchy of state machines. Our state machines controlled each of the functions necessary to perform the ball sorting algorithm and correctly ordered their timing. Our state machine also encompassed 2 different styles of extra credit, which were random object localization and dynamic tracking. Both of these were accounted for at our state machine's initial design, as we felt it would be advantageous for us to design it all from the get-go and have everything present in one single loop. This did add some complexity, however it allowed us to create a much more robust system at the end of the day. Our system was fault tolerant and was able to solve errors that occurred, such as if unsafe theta values occurred at any point along our generated trajectory. The final advantage of this was that the system required no user intervention to sort multiple balls, including if they were moved and/or removed during its process. Thank you for watching. I hope you learned something and I hope you enjoyed this presentation.